We just reviewed the general steps for getting started with your new binding system, and now we will go into more details into some tips and tricks for running your experiments. Being able to differentiate between good and bad data is key for a couple of reasons. One, for determining accurate binding kinetics, and two, since these experiments can take some time, if your first set of binding curves don't look ideal, you'll want to stop the test instead of spending more valuable time getting unusable data. Now, for fitting data, we usually start with a simple one-to-one binding model. Now, for this binding model, accurate binding constants come from simple exponential binding curves in the association phase. So it is important that the centrograms have curvature and are not just straight lines, as these straight lines in the association phase could either mean that you are only sampling the very initial linear portion of your binding curve, or you are working in a diffusion limited regime. And I'll touch upon this a little more later. Now, both of the curves on the left-hand side show nice curvature in their association phase, but differ in terms of their dissociation phase. On the top set of curves, the interaction has a relatively fast dissociation, and we see that the sensor signal comes back down to baseline as before the analyte was introduced. So this means that all of the analyte is dissociated on its own, and a regeneration step would not be needed. Now, in the bottom set of curves, you can see that the dissociation rate is very slow, and the analyte is staying bound to the ligand. So in this case, a regeneration step would be needed between each set of concentration injections. Now, in the set of curves on the bottom right, this is an example of when a bulk shift is present in the data, which happens when the analyte sample buffer and the running buffer do not match. And this can be characterized by a sharp increase or decrease in the data at the very beginning and very end of the association phase. It is usually more prominent at the end, as it looks like there's a disconnect in the data. However, this is actually a false signal. Now, you can correct for the bulk shifts in the data within the kinetic fits, but we always encourage that you try to reduce this effect as much as possible experimentally, so that you can have the highest confidence in your kinetic data. Now, as I said, we normally start with a simple one-to-one binding model for fitting our data. However, there are much more complex binding models available that can be used for the kinetic analysis, but I will caution you about using these. Some people try to fit bad data to more complex binding models because they will always fit better due to there being more parameters for the data to be fit to. Now, you should avoid using these complex models unless you have previous evidence, whether through literature or other biophysical techniques in your lab, that show your interaction is in fact more complicated than a one-to-one. Sometimes exact matching of the analyte samples to the running buffer is impossible. However, we can use a reference channel to correct for this, as shown in the example below. In this instance, we have our channel 1, which is our reference channel, and our channel 2, which is our active channel. And we see that the signal that we've detected in either channel. So the signal we detect in channel 2 is corresponding to the binding of our analyte to our ligand. However, we also are detecting a signal in channel 1, which is corresponding to the bulk shift due to the mismatch between the analyte and the running buffer. Now, because we're using this reference channel, we can actually correct for that bulk shift by subtracting that signal from the blue signal, which will now give us our corrected signal, which corresponds only to the binding of our analyte to the ligand. Here I am now going to touch on a few pointers about optimizing your analyte binding curves. So as mentioned earlier, during the experiment, you can collect as many different concentrations of binding curves as you'd like. But for the data analysis, you want to choose between 2 to 5 curves to use. And again, as mentioned earlier, you want to make sure that the samples are being used in a concentration range between 0.1 times and 10 times the KD of your interaction. Now, on the bottom left, you can see that if your range is too high, or on the bottom right, you can see if your range is too low, then you won't be able to calculate an accurate KD. You also want to ensure that you have nice spacing between your binding curves. And to achieve this spacing, as mentioned earlier, again, you're going to want to work with either a 2 or 3-fold serial dilution. And again, as a reminder, you ideally want to have nice curvature in your association phase. So for this, we typically recommend running your analyte injections at a lower flow rate to achieve a longer interaction time. And now during the binding test, you want to be starting with the lowest concentration of analyte that will give you a curve. So in this case, it'll be at the 0.1 times Kd, and then you're going to increase the concentrations from there. The reason behind this is that it tends to be easier to dissociate lower amounts of bound analyte from the sensor surface, and your regeneration steps will likely run smoother. Now, what is nice about these experiments is that you're going to be fitting all of the concentrations sampled to one binding model to obtain one set of binding kinetics parameters. Now, that means within the model, each concentration that you are sampling is acting as a repeat for the others. So this means that you don't have to repeat each concentration in triplicate throughout the test. However, we do recommend picking at least one concentration to repeat, and this is more so just to ensure that the binding capacity of your ligand isn't changing over the course of the test. So in the example shown here on the bottom right, what we have here are 3 sample injections of the same analyte at different points throughout the test. And this nice overlay of the curves suggests that the binding capacity of our ligand is remaining constant throughout the whole duration of the test. Now, another thing to note is for the dissociation phase, you want to ensure that you have a long enough collection of data that at least 5% of your analyte has dissociated. Now, sometimes this might take 2 minutes, and other times this might take 15 to 30 minutes. To calculate this, you're going to watch the response graph to see the amount of decrease in the signal. As with any flow-based system, it is good to keep in mind potential mass transfer effects. Typically, for most applications with the open SBR, you don't have to worry about this unless your interaction has a very fast on rate, faster than the diffusion of the analyte from the bulk to the sensor surface. If this is taking place, typically you will see straight lines in the association phase. Now, if you do experience mass transfer effects, don't worry, as there are a few things you can do. The easiest is to use a diffusion-limited analysis model that is available in TraceDrawer. However, as with the non-specific binding test, we always advise trying to reduce these as much as possible experimentally before trying to fit your data. And experimentally, this can be done by running at a higher flow rate or lowering the surface density of your ligand. Cleaning and maintenance of the open SBR instrument is also key for obtaining good data. Now, luckily, this is very simple with the open SBR. We have no cleaning or maintenance contracts with you. We do have 3 simple procedures, all of which that are outlined in detail in the operations manual for you. Now, the most important one out of these would be the post-experiment procedure. Now, regular maintenance of the system will ensure that the machine is functioning properly and will always continue to provide the highest quality data. This will also prevent any issues that might occur, such as clogging or poor performance of your SBR instrument. Now, we do have prepared maintenance kits available for purchase if you would like to buy them through us. Now, one thing to note, if you do ever experience a clogging of the tubing, all of this troubleshooting can be performed by you in-house. All we do is ask that you please contact us so that we can guide you through the appropriate procedures safely.